Okay, in this video I'm going to be talking about problem 6.50 from the Pearson book, which was number 16 in our chapter 6b homework assignment. This one asks, what's the ratio K1 over K2 when K1 is the kinetic energy converted to internal energy when two cars, each initially traveling at 88 kilometers per hour, collide head on? And K2 is the kinetic energy converted to internal energy when a single car, moving at 88 kilometers per hour, hits a stationary car. Okay, so we got two different situations of a collision, one where both cars are moving and one where one is stationary and the other is moving. And we're figuring out how much energy is converted to internal energy in both of those collisions, assuming that the collisions are totally inelastic. So that tells us that they're going to stick together and move together if they move. And we're also assuming that both cars have the same inertia. So it's two identical vehicles. Okay, so let's copy some of this information down into our collision tables. So we've got one inertia. I don't have numbers for any of these things. I'm actually going to try and kind of cheat a little bit on the units and say we've got one inertia unit for one vehicle and one inertia unit for the other vehicle. So they've got equal inertias. And the velocities, I'm going to say, are 88 and 88. Actually, I don't even want to do that. I don't like dealing with these numbers. Let's say we've got V and minus V. So this is the original situation with the two cars about to hit each other going equal and opposite speeds, head on 88. Okay, so in that version of the system, the total inertia of the system is 2. The momentum is V and minus V and 0. So in this reference frame, the system has 0 total momentum. So we're already in the 0 momentum reference frame for this first situation. And this is where we're talking about K1. And then the total KE is 1/2 times 1 times V squared, which is in symbol form V squared over 2. And then this one is also V squared over 2, which makes the total kinetic energy V squared. And the relative speed is 2V. Okay, this is a before table right here. Before in that first situation where both vehicles are moving. Okay, let's think about after from that same point of view. So same point of view, K1, where originally the two cars were coming head on. Okay, in that situation, we've got 1, 1, 2. What's going to happen if it's totally inelastic? We don't really have to do a whole lot of calculation here. We know if it's totally inelastic, they stick together. And if the total momentum is 0 to begin with, the total momentum has to be 0 afterwards. The only way you can have one object that has 0 momentum is if it's not moving. So that means the velocities are both 0 afterwards. And then the momentum is 0 and 0, so the momentum is conserved. And the relative speed becomes 0 because they're stuck together. And the kinetic energy is 0 and 0 and 0. Okay, so that means the amount of kinetic energy that was converted from kinetic energy to internal energy was all of it. Okay, in this particular reference frame, in this collision, 100% of the energy was convertible, and because E equals 0, it's totally inelastic, all of it was converted. Okay, so we've just figured out what K1 was. K1 is V squared in this scenario. Okay, now let's think about the other collision. The other collision, one of the cars is stationary and the other one is moving. So that one's moving, this one's stationary. So we've still got masses of 1 and a total of 2. This is a before table. The velocity of this one is V because it's also moving at 88 kilometers per hour, and this one is 0. Okay, one thing to make sure of right here. These are not two different perspectives on the same crash. These are two different interactions because the relative speed isn't the same. Because the total momentum, well, I mean, the total momentum can be different in different reference frames. But what's the relative speed here? The relative speed is v, and originally it was 2v. The relative speed doesn't change in different reference frames because the difference between velocities is the same for every observer. So this is not, to repeat myself, not two different viewpoints of the same thing. This is two different things. And we're trying to compare these two different things to each other. So it's probably going to be kind of obvious that there's less energy converted into internal forms in this second scenario than in the first because there's going to be less energy to begin with. There's actually another subtle reason for why there's less energy converted. So let's keep going. So the momentum for this other situation is v and 0, and the total is v. So it was 0 before. In this other situation, the momentum is v. And then the kinetic energy is 1/2 times 1 times v squared, which is v squared over 2. And this one's 0. So the total is v squared over 2. Okay, so this scenario has half as much energy to begin with as the first one did. Okay, but let's figure out what happens afterwards in this scenario. So in the K2 situation, after, so we've got inertia of 1 and 1 and 2. Well, they stick together, right? They stick together, but because the total momentum wasn't 0 to begin with, they're going to be moving. What velocity will they have? Well, in order for the mass of 2 to have a total momentum of v, that must mean they're moving at v over 2. V over 2, v over 2. So that the momentum is v over 2 and v over 2, and the total momentum is v over 2. Ha. No, not v over 2, v. Ha, again. That's the only way that you can make the momentum be conserved if they're stuck together, is have the velocity get cut in half. We've seen that in a bunch of other kinds of scenarios. Okay, so the subtler reason why there's less kinetic energy converted in this scenario is that there's momentum in this scenario. And because that momentum has to be conserved, it can't change. And so some of the kinetic energy has to remain as kinetic energy in order for things to still be moving after the collision. So relative speed is 0. The kinetic energy is going to be 1/2 times 1 times that squared, which ends up being v squared over 8. Let me write that out. 1/2 times the mass of 1 times v squared over 4, which works out to v squared over 8. This one is also v squared over 8 because it's the same inertia and the same velocity. And then the total kinetic energy is v squared over 4. Okay, so in the first scenario, we had a delta KE. And actually, let me just make this bigger for a minute. We had a delta KE of v squared. That's what K1 was. In this second scenario, we've got a delta KE of v squared over 4. That's how much was converted. So in the first scenario, 100% was converted, and that number was v squared. In the second scenario, only 50% was converted, and that number was v squared over 4. So the reason only 50% is converted is because there's momentum here. That momentum has to stay momentum, so there's a kinetic energy that has to stay kinetic energy. Okay, so then the question is to find the ratio of those two things. So we've got K1 equals v squared, K2 equals v squared over 4. We are being asked to divide those two things to get K1 over K2. That's going to be 4. So in the first scenario, 4 times as much energy gets converted into internal forms because there's twice as much energy to begin with, and 100% of it gets converted. This is related to a question that often comes up about, is it the same thing to have 2 cars coming head-on versus 1 car stationary and the other one coming twice as fast? There's a Mythbusters episode about that. So think about how this question and this relationship between this scenario and this is related to that other question. It's not quite the same because the velocities are different in that other imaginary scenario. Okay, so in any case, to finish this up, the number I want here for that ratio is 4. 4 times as much energy is converted in the first scenario than in the second. There we go. Thank you.